Okay, let's start, Professor Reddy.
Good morning to all of you, and I welcome all of you to the 11th day sessions of Faculty Development Program on Shallow and Deep Foundations, being organized by the Department of Civil Engineering, Andhra University College of Engineering, under the AICTE Quality Improvement Scheme. So during the morning session, we have lecture by eminent Professor M.R. Madhav on the topic of ground engineering for foundations in weak or soft soils. So I hope all of you have enjoyed the Holi festival yesterday, following the COVID-19 regulations and all. Now I invite Professor M.R. Madhav sir to deliver his lecture. Please, sir.
Thank you, Professor Reddy. A very nice morning to all of you. Can you permit me to upload?
Sir, 1 minute, sir. I'm starting.
Trust all of you had a wonderful Holi, enjoying. Is the screen visible, Professor Reddy?
Visible, sir.
Okay. So very nice morning to you. And again, I'm very delighted to share some of my works and presentations with you. And this is one of my favorite topics, which I've been teaching since last maybe 45 years. At IIT Kanpur, we started this course way back in 1975-76. You'd be kind of intrigued why I'm calling it doctrine / engineering of soft or weak ground. You know, when I became interested in working on weak and soft ground, I realized that you had to be more like a doctor than an engineer. The diagnosis is very important. Once you know what exactly is the problem, then you can think of the way you can treat the ground. So here, I treat the ground like a human body. When a doctor examines the human, whether, somebody says, I have pain, I have fever, I have something else, he has to find out which exactly is causing the problem. And that is also very similar for the particular case, because very often I'm invited to some of the sites. Most recent one was one in near Hyderabad, where there was so much of overblasting that one corner of a building foundation got heavily damaged. And on one side, it's a 6-8 meter deep cut. And they have one level of towers, and on the top of the fractured rock, they have another tower coming up. They were looking at it as if it's a bearing capacity problem. Whereas when I went and I visited that it's partly a slope stability problem, because the fractured rock is not stable, and the tower on the low-lying area needed to be protected from the instability. There was a certain weakness in the foundation that we could easily correct by kind of redesigning the foundations. So the problem here was diagnosing what exactly was the problem. So as you go along, I'll show you some parallelities why at the end of the day, when you're dealing with all the difficult ground problems, you have to be more a doctor in diagnosing the same. Topographic map of India. I think you probably know the kind of regions. We have a long coastline. We have the pink area is the expansive soil in the Deccan Peninsula. The green one you can see is the Indo-Gangetic alluvium. Then you have the Sivaliks and Himalayas, which will give you a lot of border deposits. The green part of it on the left is the Thar Desert, which is in Rajasthan, and then you do get some of these what you can call hilly areas down south too. So I normally convert that into a geotechnical map of where you can see that we have about 5 to 6,000 kilometers long coastline, starting from Kandla here, then you end up getting Surat. In between, of course, you have Bhavanagar, etc., Bombay, Goa, Cochin. Then on the east coast, you end up getting Tuticorin, Chennai, and now Krishnapatnam is here, Vishakhapatnam, and probably one or two new will come in Andhra Pradesh. Then you get to Paradeep in Orissa and Haldia. Now, all the coastline soils, which are extremely soft, extremely weak, and also they take a long time for consolidation. And most of the challenging jobs are here because all the development, shipping industry, manufacturing, etc., are on these deposits. So we do end up getting one of the most challenging jobs on this. This Deccan Plateau, which was originally a basaltic rock, has got decomposed and weathered into what you call as a black cotton soil. Of course, as a geotechnical engineer, you will say it's an expansive soil or a soil which is subjected to volume changes depending on the season. We have the desert sands here on the west coast, Rajasthan, in western part of India, and southern part of Punjab. Some of the interesting problems I found were collapsible soils here. When you saturate them, they collapse. This inorganic alluvium is a very, very broad term. If you say it's one type of soil, you're mistaken. The only thing is all the soils have been transported from Himalaya by the glaciers and the rivers. The rivers coming from the melted glaciers. If you start looking for the kind of material near Haridwar, it will land because by the time it crosses Rishikesh, the gravel is all deposited. So from coarse sand, by the time it comes to Aligarh, the Narora power plant, you get fine sand. By the time you come to Allahabad, Varanasi, it becomes a silt, clay silt or sandy silt. By the time we reach Patna, it becomes clay silt. And by the time you reach Howrah and Haldia, it becomes more of silty clay. So the grain size distribution keeps changing. And the type of, even though you call alluvial, it's not the same. The same thing is true of Brahmaputra Valley. You find the grain size decreasing by the time you reach Hooghly and by the time you go to Bangladesh, etc. Then we have these laterites along the west coast, starting from southern Maharashtra, Goa, Konkan, and right up to Kerala. Then you have small stretches of these laterites in the east coast too, and then of course somewhere in the Chota Nagpur area. The most difficult sign which we cannot be easily characterized are the boulder deposits. You know, huge boulders have been transported and deposited by the glacier. There's no way you can test them because you can't drive a borehole into that, but we had to have some difficult challenges there too. Add to that, we have the seismic map of India, and you can see, fortunately, down south, we all have only zone 2, which is the very low intensity earthquake. You probably designed for magnitude of 3, 4, at best 4.5. Then you have zone 3, and as you go this again at best you have a seismic coefficient of 0.12 to design for. The green and these colored ones, which are zone 5, are more serious in the sense the northeast. I want you to notice also the Kutch area, Uttarakhand, part of Himachal Pradesh, Jammu Kashmir, zone 5. That is where the most difficult, very high magnitude earthquakes occur. Zone 4 also is a very serious one, but not to the same extent as zone 5. But because of so many tall structures coming up in Delhi, Gurgaon area or Noida, even an earthquake of magnitude 5, 5.5, 6 can be a serious problem, which means we'll have to deal with these seismic events or the seismic inputs while designing the foundations. When you look at a foundation type, you know that we have the shallow foundations. I put a footing and take a column. Or you can have a raft with the usual column. We can go for pile foundations. You have a pile raft. Earlier it was a floating raft, but nowadays we design it as a pile raft, so which the raft also transmits about 40 to 50% of the load directly. These deep foundations we use for bridges and heavy structures where you have large diameter piles, and maybe enlarged, but most of the time now we don't enlarge. What I want to show here is that when I look at any project, we divide the structure into three: light, medium, or heavy. Light means it's basically 1 or 2 story light structure, which may transmit average bearing pressure of maybe around 78 tons per meter square, 70, 80 kilopascal. Medium is what I call as something like 5 to 7, 8 storied one, where the average stress which is transferred to the soil could be on the order of 15 to 18 or 20 tons per meter square, or 150 to 200 kilopascal. Heavy structures are those industrial plants, high 30, 40, 50 story buildings, houses, and the kind where the loads are heavy and very, very large at each location of the column or the support system. Similarly, I look at the ground, I classify that into soft, medium, stiff, and hard. Soft is our typical marine soils along the coastline, which have very low strength of the order of maybe 10 to 12 kilopascal and drain strength. The compression index is after 0.5 to 0.8. Coefficient of consolidation is around 1 to 2 meters square per year. The medium stiff soils are the alluvial soils, which give me easily bearing capacity of 10 to 15, 20 without any problem. If I go deeper, it's better. Hard soils are the ones we end up getting in most of Hyderabad, where you have hilly terrain, parts of Pune, Bangalore, etc., where you have fairly strong, hard material at shallower depths. For example, in Hyderabad, I find that if I go to 5 to 6 meters from ground level, in many parts of the city, you will get a very good hard stratum, which can take 100 to 150 tons per meter square. So in this matrix, if you have a light structure on a soft ground, you can get away with either shallow foundations or ground improvement. If you have a medium heavy structure on soft ground, you don't have to go for deep foundation. Why I'm making this issue is deep foundations mean pile foundations, well foundations, etc. Though I don't recommend wells anymore because they're very difficult to sink and very difficult to construct and highly conservative in terms of design. That's a separate issue. I can talk for an hour on that alone. And I would like to avoid deep foundations because the cost also. I think you should know that piling costs around 8 to 10,000 rupees, and you need huge machinery and installation. So if you have a medium structure, heavy structure on soft ground, you can simply improve the ground and then get away with it. If you have a very heavy structure on soft ground, there is no alternative to deep foundation because the soft ground, even if you go maybe 5, 10 meters, you will not be able to get adequate bearing resistance, though we try to do some kind of semi-floating foundation. You have medium stiff ground, light structure, shallow foundations, no problem at all. Medium heavy structure on medium stiff soil, you can again get away with medium ground improvement. Heavy structure on medium stiff ground, you either have to go for deep foundations or ground improvement. If you have a hard ground, hard stratum, no problem. We can get away with shallow foundations most of the time or with little amount of ground improvement for the deep, medium or heavy structures too. So basically, it tells me that the conventional idea of shallow and deep foundations, you have to know intersperse. I had one more parameter that in between these two extremes, we can modify the ground. We can improve, we can strengthen it so that we avoid as much as possible deep foundations. So this is what basically the options are. You have shallow foundations here, you have deep foundations. There is a very interesting option our ancestors did. They removed all the difficult soil and filled it with more completed one. You may think it's crazy, but if any of you have visited Warangal, both the Thousand Pillar Temple and the Ramappa Temple, over a depth of 8 to 10 feet, the black cotton soil has been excavated and replaced with very good dense sand. But this sand did also settle over a period of 800 years. So some parts of Thousand Pillar Temple are being reconstructed. But what we can do is I can replace the difficult ground with stone columns, drains, etc. So this is what I call as a practice. And if you look at the foundation engineering practice now in the country, a majority of difficult sites are being treated with ground improvement methods, and people avoid pile foundations unless it's absolutely necessary. What are the kind of common problematic ground conditions? As I said, soft clays all over the coast and somewhere inside too. Loose sands you find in the Indo-Gangetic alluvium and also in the Brahmaputra Valley. Expansive soils, as you know, are available, are existing all over the Deccan Plateau, starting from parts of Madhya Pradesh, Maharashtra, even Gujarat, Saurashtra has a lot of expansive soils. Then, of course, Karnataka, parts of Tamil Nadu, Andhra Pradesh, Telangana, etc. We have these expansive soils. The collapsible soils, which are very rare relatively, but we do have some solute problems. We had dealt with a couple of sites in southern Punjab, a place called Faridkot, where the structures were all built in 1920. They were fine till about 1975. And after 40, 50 years, they suddenly started collapsing. The reason was the groundwater table rose from a depth of something like 90 feet in 1915 to as close as 1.5, 2 meters from ground level because of, seepage from the irrigation canals and various other reasons. So the structures collapsed because in a dry condition, the soil is very strong and stiff. Add water from groundwater rise, the chemicals got dissolved and the structure collapsed. Seismic conditions, as I told you, are available all over the north. See serious ones in the zone 4 and 5. Even in zone 2 and 3, we do design for the earthquake conditions, but we don't have to worry about liquefaction at all. I found artesian conditions in the what they call as Terai region. If you go to Gorakhpur, etc., where the groundwater is probably close to ground level, in some places it could probably be an artesian condition. We found one particular interesting case in near Muzaffarnagar in Bihar, where a bridge started floating because of the artesian. The next two, contaminated ground and groundwater pollution, are human-created problems. Because of our urbanization and waste generation, a lot of municipal solid waste and, of course, chemical hazardous waste is being dumped into the ground. The leachate from there is contaminating the ground and the groundwater. So we, as geotechnical engineers, are being challenged to deal with this problem too. Unstable slopes is a very perennial problem all over Himalayas and in some of the peninsular India too. In the coming rainy season, you keep hearing this failure. I think you know the recent Uttarakhand disaster in January, which is one of the most unusual ones, that a slope failed in frozen condition and led to a major disaster on one of the dams there. If one is tunneling in Himalayas, the rocks there are very, very soft and weak. So the tunnels that start squeezing into the cavity and lead to trouble. But I'm not going to deal with that at all. Now, when I want to things, I want you to identify. How do I identify a soil is soft or not? So if I have a fine-grained soil, the first simple thing I look for is the SPT and value. If N is less than 2, I call it as very soft because the underlying strength is less than about 12 to 13 kPa. the uh, index of that what you call CI is less than 0.5. If N value is more than 2 to 8, you have to call it a soft to medium, and the underlying strength could be anywhere to 40, 50 kPa. If it is 8 to 15, N value is 8 to 15, we call it as a stiff soil, and then the underlying strength is 40 to 75 kPa. Here the value given is unconfined compressive strength. So if I look at underlying strength, it is half of that. And if you have N value more than 15, just take it easy, you're happy, the soil is very stiff, it's not going to give you any major problem. If it is more than 30, obviously, it's a very hard stratum and again, very safe. And then I look at natural water content. If the natural water content is 70, I get worried because the compressibility is very high. If you look at this chart, around 80, the CC by 1 plus E naught, what we call as compression ratio, is the order of 0.2, 0.25 to 0.3. And the sediments could be an order of even 1 meter depending on the thickness of the stratum. And the other thing I want you to remember is if you're dealing with soft clay, try to get the natural water content. That gives you a very good handle to identify the seriousness of the problem. The problem with many of our investigation agencies is they collect a sample and determine the water content after a week or 2 or even 3. One side where I went, the water content according to us more than 85, which is what we found out immediately. But the investigation agency gave us a value of 27. I asked them why. They said we had to send the sample from here to Chennai. It was tested and they didn't seal it properly. And you can't keep it for 3 weeks. The water will escape and dry. So try to get the natural water content. Find out what is the liquidity index. If it is close to 1, we have serious problem because it's extremely soft, very close to liquid limit, and so problems too. When I have sands, again I could depend on SPTN, and you can see that depending on whether it is fine, medium, coarse sand, and the N value, you can identify the relative density and the state of the sand. It can be very loose, can be loose, medium, or dense, or very dense. So when N values are less than 10, I find it very, very loose to very loose condition. And if it is more than 20, I have no worry, because then the soil sands are 20 to relative density is more than say 65 to 70, etc. And here again, I want to give you a simple rule. If N value is less than 10 for a sand, you can end its in seismic area 4 or 5. Possibility of liquefaction is very high. If N value is more than 20, you can feel sure that liquefaction is most unlikely. Between 10 and 20, I take a more serious view of the same. And again, you get an idea in terms of the angle of shearing resistance. Again, you can see that if I have medium dense to dense soil, the angle of shear resistance is 35 to 40, 45, and you have no problem at all. Similarly, we can identify the expansive soil and just of it. So if I have the fines content, particularly the clay content on the x-axis, and activity, which is nothing but the PI divided by clay content, you have the chart on the left-hand top. You can easily find out whether the expansive soil is of very high seriousness, high, medium, or low. Depending on that, you can immediately decide what can be done. Similarly, I use another chart where I have the clay content versus the plasticity index. So when the clay content is more than something like 30 to 40%, and plus more than 30 to 40, then I'm worried. Otherwise, I find that it's not a much serious problem. I want you to realize that just because there's a black cotton soil, people keep running around saying that's a very serious problem. Not all black cotton soils are a serious problem, but it depends on the clay content, plasticity index, and activity. The more important thing I want you to remember, black cotton soil by itself is not a problem. Only when you allow access to water, then it keeps changing in volume. So what I'm now trying my practices is that I try to maintain the water away from the soil by proper drainage measures or surface measures wherein water does not enter into the building site or near about it, then I have no problem at all. So then we don't have to worry about black cotton soil. Collapsible soils, we have a lot of these criteria wherein you find out the dry density versus liquid limit, and if you particularly for only wind-blown deposits. Don't worry about ordinary alluvial deposits. One or two weathered soils also collapse, but that's a very rare instance. So using this chart, we can easily find out what could be the possibility of soil. This is our golden rule as far as seismicity is concerned. You can see that I have SPTN versus cone cyclic resistance ratio CRR, which is obtained for the type of problem we have. And if you look at it, N value is less than 20. If N value is more than 20, there's no liquefaction. The point that you see on the left side are where liquefaction has occurred. Again, the second thing is the fines content. If the fines content, that means silt and clay is less than 5%, liquefaction is very high. So the 5% curve is to the right, 15% is to the left, and 35% is even much to the extreme. So you can see that if you have N values less than 10, it's a very serious problem. 20, very little problem, and 10 to 20, you have to think of some intermediate values too. And in all ground improvement, I want you to be a doctor in this sense. When one is not doing well, he's sick, he goes to a doctor, he prescribes a medicine and asks him to see him after maybe 3, 4, 5 days. And then if one is cured, he says thank you and you pay him the fees and say come back. But if one is not cured, he changes the medicine, he may change the dosage, or even whole process of treatment he can change too. In ground engineering or geotech practice, we do exactly the same. You have to compare what was the condition before treatment and what treatment you have achieved. Without that, you cannot be 100% sure. Ground is a very complex entity, which means whatever I suggest may work only half the time, or may not work at all. So you have to be very careful. If with time, of course, your judgment improves and you're able to predict what is likely to happen, but validation is very important. You have to ensure that whatever you're suggesting is being achieved in the field by observing the behavior. I'll show you how we do that. So if I'm how to deal with the ground, let's look at two basic categories: fine-grained soil, coarse soil, and granular soils. When I say coarse soil, basically I'm looking at silt, clay, peat we don't have. Subsoil again is a typical Gulf type of material. The most common approach for us is to have preloading with vertical drains. And now we are, instead of surcharge, we are going for vacuum consolidation. In case of granular soils, we need to have some dynamic method, vibrations. It could be heavy tamping, dynamic compaction, or a vibro compaction. We can now think of an improved version of not only improving the soil, but reinforcing it or strengthening it, that by adding some material. If you look at the first set of 1, 2, 3, 4, you find that you're not adding any material, you're only improving the ground conditions. In the second variety, you can have dynamic replacement. I push on the granular material into the ground by heavy tamping. We can have stone columns using vibro needle. We can have control modulus columns, which means I can inject cement or lean concrete instead of granular material. The last one is a very powerful, wherein you can inject cement at very high pressure, dry jet, and the ground becomes very strong and stiff. Let's see these particular cases. I would like to illustrate them with different case histories or mechanics and procedures. As I said, the cheapest and the best for most soft clay is preloading with prefabricated vertical drains now. In the good old days, we had sand drains, which are time consuming to install. Now we have PVD, which I can install within a minute or two over a depth of 12 meters. I have soft ground. I want to put in a light to medium structure, like, a residential office building, etc. This is likely to settle. So what I do is, in order to make sure the settlement occurs, we put a dummy load. I call it as an embankment surcharge, and allow the soil to consolidate. Once the soil consolidates, remove the surcharge, and then you construct the building. The analogy I would like to give is that all of our children, students, they take a mock test, whether it is a 12th board, 10th board, or JEE. Every coaching institute does it. Why does it do? Because once you go through a dummy, your performance in the real one will be much better. So preloading is exactly like your mock test that you do in all of this. What does it do? You know that these soft clays have very high water content. I was mentioning to you around 80 to 90, 100%. So the void volume is very high. For all you know, the particles may not always be in close touch with each other. So because of that, you need to bring them together. So when you put extra load, remove the water through consolidation, the particles come closer to each other, the effective stresses increase, and the settlements become much less. So this is the concept that we do. I put suppose I want a bearing pressure of something like 78 tons per meter square. I find out equivalent weight of the embankment, maybe 4 to 5 meters, and add a little more so that in a shorter period, I can get more consolidation. Now, if you put the embankment load and the surcharge without treating the ground, the only way the water can escape from the soil is by vertical, downward and upward flow if you have drainage boundaries on the top and the bottom. This is going to take a very long time. For example, if you have even a 6-meter thick soft clay, it may take 10 to 15 years to get 90% degree of consolidation. And the principle, as I said, I put the surcharge, the settlement will occur here during the period of surcharge. When you remove it and put your regular load, it doesn't at all. So whatever settlement you're anticipating is being achieved with a dummy load. And if you put large surcharge load of, say, 5 to 6 meters, 7 meters, you will end up failing the soil because soil cannot handle that amount. So what we do is we normally increase the surcharge maybe over 2 to 3 meters at each stage, wait for a month, 3 weeks, and then keep on adding so that the soil is consolidated in that period and is able to take extra load. So this is called stage loading. The most important thing that comes about is if you don't deal with the soft clay and only extra flow upward, downward together, the consolidation will take a very long time. But what we can do is provide vertical drains, which are very easy to install. So we can drive them at an interval of, let's say, 1 meter, 1.1 meter. The drainage path without treatment is around 5 to 6 meters if it is 10-meter thick deposit. Now we have reduced the drainage path to half a meter. And when you calculate the time factor, CVT by H square, so it becomes 100 times faster. Second thing we all need to realize is, in the first case, the flow is vertical, and in the second case, the flow is horizontal. I think all of you know that coefficient of permeability for most natural deposits is more in the horizontal direction than in the vertical direction. So because of these two reasons, the coefficient of consolidation for radial flow is at least 2 to 5 times more, and the drainage path is being shorter. You will end up getting 90% degree of consolidation under embankment surcharge loading to within 90 to 120, 150 days, which is what most projects are very happy. Once you introduce these drain, you need to get so that the water that comes from the drain gets collected here and you take it out into the ground. So basically, this is the way in which you expect the preloading with vertical drains to function. The preload will induce high pore pressures. The pore pressures get dissipated by flow into the vertical drains, and vertical drains take the water to the top, and then it goes out to the same. So this is how the whole process takes place. And here is the bottom one, which will tell you would have had a long time for consolidation. With drains, you probably will achieve within 90 to 120 days all the settlement that you expect. This is simple stages in the preloading with vertical drains. One particular airport you want to construct. For example, this is one of those at Incheon. Soft clay, you provide a embankment of the drainage layer, install the drains, the settlement occurs, remove the surcharge load, which is above the ground. Quite a bit of settlement can take place, maybe the order of 1 meter, 1.2 meters. Then you construct your airport on the top. I want you to see what happens in the E-Lock graph. Initially, the original stress is 0.1, 2 gives you the maximum fast consolidation pressure, the PC, and when you load it with surcharge, the point moves from 2 to 3 due to consolidation under the preload. When you unload, where is it going though? Okay, the unloading gets you to 4, and when you reload with your structural load, the settlement is only from 4 to 5. And that means which is very, very small. And how we do that? We have 2 patterns of drain arranging these vertical drains. We have square pattern where the spacing is the same in both the X and Y direction. Very easy to install according to the operator of the crawler mounted machine. If you have a triangular one, which is a staggered one, you find that the area covered is much better. What we try to do is find out the influence zone, or what we call as a unit cell. In case of a square, the zone of influence is a square. We convert into a equivalent circle, the diameter of which is equal to 1.13 times spacing. But if I have a triangular pattern, I can convert the zone of influence into a hexagon, take any 2 adjacent drains, and half a point is the zone of influence, and becomes a hexagon. If I convert into a circle, the diameter is 1.05 times that. The PVDs are like stitching machine. They go into the soft clay 10 to 14 meters within maybe 1 to 2 minutes. This is how the site may look like. After the installation, all the drains have come out, and you can see the drainage blanket on the top. How does the PVD look like? It has 2 components. One is called the PVD core, which is made of polyvinyl polypropylene. It actually provides the drainage channels. It gives strength to the drain, it does prevent buckling, and it supports the filter. Filter jacket is a non-woven geosynthetic. It allows the water to go through, but does not allow the fine particles. Also, it tries to resist the lateral pressures, which is the horizontal component of the pressures in the ground too. So the drain is very easy to install. In the good old days, we were using a lot of this embankment loading. One classic case I would like to tell you is the Salt Lakes area in Calcutta in 60s. It was purely soft clay, and you'll be surprised now, one of the most expensive areas in Calcutta. We do all over the country, we have been putting dummy load, but nowadays transporting, let's say if I have 1 hectare, 10,000 square meters, and I had to put in 5-meter fill, it becomes 50,000 cubic meters. If a truck can transmit 8 cubic meters at each trip, I need something like 6,000 truck trips. That's enormous transportation of material, fuel, pollution, carbon footprint, etc. What they found now is, why not use pressure, and we create vacuum. We're using vacuum in many engineering situations, including brakes. So similar to that, if I can provide a membrane and create vacuum in the ground, I can get the atmosphere itself to apply pressures. You know that atmospheric pressure is 1 kg per centimeter square, which is 98 98.4 kPa, but we don't go up to that. We stop around 85 to 90 kPa free. Additionally, you can put a little surcharge if necessary, and this is one of the most popular techniques. Now, if you have a large area to be treated, improved, the best is go for vacuum consolidation. There are two ways in which you can do. You provide a membrane and seal it with all this water trench, etc. Each drain is connected to the vacuum pump directly, as you can see in this one. So vacuum is applied to the drain itself and the water is sucked from inside the ground. One of the most classic first project that was done was when Airbus 380 was being constructed. They had Airbus industry had to develop a site in Hamburg. Originally it was a lake deposit and they had to improve it, and they had to produce the planes within a very short period of time. That is when they installed this vertical drain and then did vacuum consolidation. And you'd be surprised. Within a matter of 2 to 2.5 years, the factory was ready and they could produce the Airbus 380. And this has been adopted all over the world, wherever you can afford to do that. How do I monitor? I install instrumentation in the ground and I can measure the top one gives me the loading. Embankment load is built in, and we measure the settlement. And you can see that once the settlements kind of terminate, you know the 90 to 95% of consolidation is over. We can easily verify that by putting simple settlement plates on the ground and measuring. I want you to see in this particular case, kind of settlements are of the order of 2 to 4 meters. That's the kind of ground you are talking about. You can also monitor the pore pressures inside. If it is a surcharge loading, you will get positive pore pressure. And if it is vacuum loading, you get the negative pore pressure, as you can see here. This is the negative part. Then it becomes zero gradually. The advantage with vacuum preloading is that under surcharge loading, while settlement takes place, there's going to be lateral squeezing, lateral displacement. With such vacuum loading, which is hydrostatic, there is no such problem. And you may end up actually getting a crack because the soil is consolidating laterally also. These are the piezometers and settlement plates that have been installed at any site. And this is a typical embankment with all the elements that are done. You have, transducer settlement plates. We are now able to measure settlement at depth, various depths, which is another aspect which you can do. The AIT, Professor Bergado, has even adopted thermo-PVDs wherein he can heat the soft clay so that permeability increases. And he finds that he can consolidate it much faster than without temperature. Then you are also combining the vertical drains with some kind of ground improvement like cement column and stiffened columns, etc., which makes a much better option. So that you can see all the settlement is achieved of the order of something like even 300, 400 millimeters with these preloading and DCM, etc. That's how they can be done. Sorry about it. When I have, you can hear me? Professor Reddy?
Sir, you are audible, sir.
Yes, audible?
Audible, sir. Audible.
Thank you. Okay. When I have loose sands, I need to apply energy. I can do by means of dynamic compaction, impact, or vibratory plate. This is how we do inside the ground, wherein we provide a probe and vibrate it so that I can densify. Blasting is also used, but you have to do it at great depths. This is heavy tamping. Imagine your Proctor test, multiply it by scaling of 1,000 to 10,000 times. If I can drop a weight 10 to 20 tons in mass over a height of 10 to 20 meters, the energy we transfer each blow is 200 ton meters to 400 ton. and the soil will get densified very fast because the energy travels radially outward, and that's what you find is the best way to densify. At the impact, you will see the kind of blow that's happening, and what we do is a primary compaction, then we go secondary, and finally we go the ironing path. The whole area is being densified over the treated area, and you can construct whatever structure. It's very easy to design what it is. The depth of influence of any blow, I mean, the treatment is roughly half of weight of the ponded drop to the power of 0.5, and we can easily calculate how much weight I had to drop or what height. And then in order to make sure that the kind of vibrations don't affect it, we have another design chart for that too. This is what happens to the ground. You will find that the layers at the top get densified much better than the ones at the bottom. This is how the surface will look with a lot of these craters, and that's how the densification takes place. A typical example is the NTPC project in Kerala, Kayamkulam. Original site is backwaters, this kind of pond or here, which you have filled with sand as a replacement. But the one below that you can see, the N values are all less than 20, less than 10. So they had to densify this so that you get a big thermal project at the site. This is how the stratification will look like. See that? You can see the hydraulic fill is about 1.5 to 2.5 meters. Then you have loose medium sand over a depth of something like 10 to 12 meters. This could be densified with heavy tamping. But before that, they put in a barge and pumped in the sand from one of the areas where they excavated sand, probably from the sea, and dumped it. This is how you fill up the site and reclaim the ground. Then here is the very simple equipment. All you need is a good crane which can lift and drop the height. The ponder here is about 20-25 tons, and then you drop over a height of 15 to 20 meters. This is how the ponder looks like. It will be a series of steel plates bolted and welded together, or sometimes you fill it with concrete as steel box and use it too. And then each blow, you find out how much is the crater depth. After some 4 or 5 blows, there will be no more densification at that point. You go to the next site and do the repeat same thing. This is how the whole process looks like. And finally, you will see the ironing pass with a very large plate, something like 4 by 4 meters. You tap it on the surface, that the surface is also densified. This is on the surface. If I want to densify at the ground, I use a vibroprocessor with a depth vibrator. You call it as a vibrofloat. You have an eccentric motor at the depth, at the tip. It starts vibrating in about a vertical axis. And this energy is transferred to the soil, and the soil gets densified. And in order to facilitate penetration, we have a nose cone here through which a jet of water is introduced. The soil becomes soft and the vibrator gets pushed into the ground very easily. This is the processor. Again, we have a crawler mounted one. Using the jet of water, we push the vibrofloat into the ground. We start vibrating it, it gets densified. Then you fill up with the soil around and complete the whole process. What you find is a loose sand has become very dense and stiff over a width of something like 1 to 1.5 meters in the whole area. So with a spacing of around 1.5 to 2 meters, you can easily densify the whole ground. The basic concept of this vibrocompaction is nothing but if I have a loose sand, the voids are very big because the particles are sitting on top of it. You can see the void space is very large. Once you vibrate it, the particles rearrange themselves, so the void space becomes very small and the soil becomes dense. It's not a big concept. Any housewife will tell you she'll buy 1 kilogram of sugar, tries to pour into a container, and container appears to be full when there is still 50 to 100 grams of sugar outside. The housewife immediately will shake the container or tap it on the platform, and then you densify the sugar. She pours the rest of it. She can do it because small container. She does it on hand. We in geotechnical engineering, we need a vibro probe to do the same. Several projects which have been densified are this GVK power project in Punjab, where the power plant was constructed on loose sand and they wanted to avoid liquefaction too. Babrala and UP, we have a packaging unit and another major project. The Seabird project in Karwar, again a very one. The Western Naval Command, part of it was shifted to Karwar, and they had to build a huge seawall by dumping a lot of sand into the sea, on top of which the wall was built. This sand, which was dumped, had to be densified, and because it's all in the sea, they had to put in a barge, and you can see 4 vibratory needles at a time densifying the whole thing. This is how they look like. And the foundation was 10 meters thick over a length of 3 kilometers, and they densified it with these vibrators. And they could densify something like 8,000 cubic meters a day. When you want to push the vibrator into the ground, you need to vibrate at 40 hertz, whereas for compaction, you need a somewhat smaller frequency of 15 hertz. And this is what happens at the jet. You get a crater and it goes very easily into the ground. Quality control, how do we do? Now all this equipment come with a microprocessor and you can see the data for yourself. I want you to see, you can get the rate of penetration, the amount of energy being consumed, and so you can get the find of column diameter, degree of compaction, etc. As the compaction increases, the power needed to densify becomes more. Same thing with the pulling out resistance too. This output to you so that you can verify whether what you wanted is being achieved or not. What we sometimes do is, if necessary, carry out a plate load test. At few places, if you can see, even with 300 to 400 kPa, you are getting hardly settlement of 20 to 25 millimeters. This is what happened to the site. Please call me after 15 minutes. I'm in a meeting. This is another way I told you, like in medicine. This is in the Karwar project. The cone penetration values before treatment were given by this orange curve. They said, no, we want something densified. So with vibrocompaction, first they got blue line, but the designer said, I want to have at least green. So then they increase the number of points and then energy that's being put in there. And so finally, you end up getting the green line. And so this is the treatment over a period of treatment that you always can control. This is another site in Yupan, I think one of the fly ash ponds too. I think all of you know that the Palm Island in Dubai was reclaimed out of the sea. All those fronts you see are nothing but sand. And this at one stage it looked like this forest of vibrocompact needles. And you can see the Palm Jumeirah, the famous hotel, on the left in the hazy one too. We use the same concept of vibrofloat, but in case of soft clays, after we get into the bottom, instead of using sand,
Sir, we are unable to hear you.
Okay, wait a minute. I'll just see.
Now it has come, sir. We are able to see you. Maybe you have to reshare your slides and start, sir.
Can hear you though.
Now you are visible and audible.
Can you hear me now?
Now it is okay, sir. Earlier for
Okay.
some time, totally your audio and video connection lost.
Okay. Hello? Connection. అవునా మళ్ళీ చూడండి ఒకసారి వచ్చింది ఇప్పుడు టెల్ మీ ఇఫ్ యూ కెన్ హియర్ మీ
Now it is okay, sir.
నౌ ఇట్స్ ఓకే
Now it's okay, sir.
ఓకే ఓకే కెన్ యూ హియర్ మీ
Sir. Sir, vibro replacement slide onwards. You have to vibro replacement.
Okay. Another case where they use stone column granular piles, power plant in Chennai, tank farm in Paradeep, a chemical plant in Gujarat. I think Vallarpadam is a classic example. The container terminal was built on stone columns where they could transfer even 200 kPa at each stage. And this is how the whole, even the warehouses were built on stone columns. One get the load settlement graph, even with 30 to 40 tons per meter square tons load, settlement is less than 10 millimeter. On a soft clay, you're able to achieve such a very high bearing capacity is something very unique. I want you to see the diameter of the columns is around 1000 to 1100 millimeters. But how do I choose between the two? If I have granular material, I can vibro compact. If it's a fine grain material, I go for vibro replacement. So this is how we do that. So in all the liquefaction studies, go for vibro compaction. And we identify which kind of soil which I can do. Earlier I gave you with SPT. I can also use cone penetration rate. And if you have low friction ratio and high penetration, you can densify by means of vibro compaction. And this is one way you can see how effective is vibro compaction. What I told you earlier, always check before and after. Before treatment, what are the N values or tip resistance and what happens to the soil after densification. So this you had to do to ensure what you want is being achieved. Please insist that we had to measure the ground performance before and after treatment. One of the best illustrations here is in Japan, there were 2 reclaimed areas which were affected by an earthquake. If you don't, the subsidence was anywhere from 30 to 95 centimeters. With preloading, it has come down to maybe 15 to about 30, whereas with sand drains and preloading, it's hardly 5 to about 20 centimeters. But vibro compaction, it became less than 5. This is the best way to demonstrate to anybody ground treatment is the best way to avoid future problems. And this is what happened to your N values. Initially, the N values were very low, 10, 12. Now it has become more than 20, 25 because of ground improvement. So you can always tell people that's the best way to do this. Then we go for deep mixing is another way you can do if you can inject it. This hasn't come into India popularly or not commonly. So it's the equipment like your starter in the kitchen. The rod is hollow and through which you inject the cement. This deep mixing is a very common technique wherein we can have one or two shafts, soil comes down into the cement comes down and you mix it with the thing. So this is the deep soil mixing rig, and this is how the completed columns look like. They work very well. Then micropiling is very common. You make a drill a hole like 100 to 125 millimeters in diameter, introduce a rod, grout it with cement. Grouting is a very popular technique in India. You can do slurry grouting like injection, intrusion, compaction grouting, thick slurry, chemical grouting, jet grouting, which is now coming to India. And for rocks, we use fracture grouting. This is how injection grouting looks like. You inject the cement, it goes into the void spaces, it becomes very dense. Compaction grouting we do to correct differential settlement, etc. Cement mortar is injected, it displaces and compacts the loose soil. Permeation grouting is where you have to fine-grained soil, you have to inject chemicals and they go into the voids and densify. And typical example is the Eastern Dam 4, where they had to do it for their underground powerhouse. Jet grouting is a much more powerful technique wherein the cement is injected into the ground under high pressure, it mixed with the soil and becomes a column and becomes very impervious and very strong. We can do a single jet, we can have double, wherein you have air and cement grout coming into, or you can have air, water, and grout. It's a triple jet kind of thing. These are the kind of gels we use. We can have soilcrete, you can have silicate gels. We can also have mortar for high, what should I say, openings like in rock. I would say the best example is our Polavaram Dam in Andhra Pradesh. The cutoff wall was dense jet grouting. This is how the whole project was. A depth of about 20 meters, the cutoff wall for the coffer dam. This is how the site was looking before treatment. You can see the river Godavari in the back. And this is how the jet grouted columns look like. It's about 2.5, 3 years old and working very well. For the main dam, they had to go for diaphragm wall, which is much more serious problem. And this diaphragm wall was installed over a full length of the actual dam site. I want you to see the most interesting thing. The deepest section is 118 meters. The diaphragm wall had to go unbelievably one of the largest depths you can think of. You have a guide wall through which you introduce the diaphragm wall. This is a cutter, which is about 5 meters wide, 1 meter thick. You can see the wire cutter and the cleaning at the bottom. This is a unit. Make an opening and support the diaphragm, the excavation before you put the reinforcement and put the cement too. And this is the exposed cutoff wall. You can see it's 1.5, 2 meters wide, and it's the best ensured so that there's no seepage below. I would like to introduce lastly to one practice which I've been doing for the last maybe 8, 10 years. I'm trying to avoid pile foundations in extremely soft ground, even for structures too, by reinforcing the ground with geogrids. You probably have studied a lot about geosynthetics. The two forms of geogrid we use are geosynthetics we use are geogrids and geocells. You can use geotextile if it is provided as strong, and you can see the geotextile, geogrids, and geocell. Geocell is where you can confine the soil. Okay, this is how they look like, geogrid biaxial one and a geocell. a geogrid interlocks the granular material, and if you can interlock it, it doesn't move, it becomes very strong and stiff. And then once you provide the reinforcement, it provides lateral restraint. So the sand above this becomes very small, not move at all. You can also intercept the failure mechanism so the bearing capacity increases. The membrane action, which means when you put the load is transmitted away from the load because of the tension in the material. And all of them increase your confinement and the load spread is much higher. I want you to see here, normal load is 2:1, but once you have geosynthetic, the load is spread over much wider area. We've calculated in some of the cases up to about 60 to 70, 80 degrees. A geocell confines the soil. So each, one-dimensional compression kind of thing, because soil cannot move laterally, it's under K-naught condition. Under K-naught condition, nothing can fail. So it becomes a semi-rigid raft, and that's how it works. So what we do in terms of foundations would be provide a number of layers, 1, 2, 3 if necessary, on soft clay over a depth of 1 to 1.5 meters and put the footing, and then the whole area becomes much stronger and transfers the load clay without any problem. The sediments are tolerable and you can have your structure. This is shared by my colleague, Professor Srinivas Murthy. He built a center school at Wellington, OT. This is a more challenging job. It's in Chandigarh, a radar tower or tracking tower, which needs extreme accuracy, was built on reinforced foundation bed. With series of bricks and geosynthetic, they could construct a mini leather. This is Krishna University buildings in Machilipatnam, where you have extremely soft clays, which are built on reinforced foundation beds. You can see that this has been in existence for the last 8-9 years, and it's still absolutely no settlement, and buildings are working well. We had another major project where they had to build in these 2-bedroom apartments very close to, again, the coast, and the whole area was highly soft with waterlogged, and they wanted this. Originally, they thought we'll go for pile foundation, which became very, very expensive. It's not possible. So then they go for reinforced foundation beds. This is the design we provided. We could get about 1.5 meter thick granular deposit because the ground also has to be raised above the original low-lying area. So we had 400 millimeter thick granular soil. We put a geogrid, some more sand, then we put a geocell, sand, and then after that PCC and the foundations. So this is how the site looks like. You can see. You fill it up with granular, compact it very well. We had fortunately 18 to 20 ton roller. The geogrid is placed here. You can see the geogrid stretched. Again, another granular layer, 300 millimeters.